In this video, we're going to discuss electric dipoles. An electric dipole is whenever you have a pair of charges which have the same charge, but one is negative and the other is positive, and they're separated by some distance d. So we're going to stick this dipole here in an external electric field. So there's some other charge somewhere else creating a uniform field that we are going to place our dipole in. So that's why I have the electric field lines drawn through here. And because they're oppositely charged, the force on one end is going to be attractive and the force on the other end is going to be repulsive. So the force in one case is going to go to the left and the force in the other case will go to the right. So that when you calculate the net force acting on the dipole, it is actually zero. Because the charges are equal, they're going to start out equal distance from the external charge causing the electric field and thus exerting the force. So the magnitude of force is going to be the same, it's just going to act in the opposite direction because one is going to be attractive, the other is going to be repulsive. However, the torque is not going to be zero because this force is going to push this way and this one is going to pull this way, or the opposite depending upon which side the charge is and what sign the external charge is. The way I have it drawn here, you're going to get a rotation that is actually clockwise, because we're intending sort of a rotation point is here at the center of the dipole. So the net torque is not going to be zero, it's going to have some value, and this is going to cause the dipole to rotate. So we're going to calculate our torque. Remember that torque was R cross F. Now we're going to do the electric dipole moment crossed with the electric field. So the electric dipole moment is the charge times the distance between the two charges. And this is a singular charge, so whatever the magnitude of the charge here is, not the two charges added together. Or we're going to do the magnitude of the electric dipole moment times the magnitude of the electric field times the sine of phi. Because remember, this gives you the magnitude, so you use sine when you have a cross product. So that'll get you the torque, and of course that torque value is going to change as the dipole rotates. So this torque is not going to be constant because it depends upon how the dipole is orientated in the electric field. So this angle phi is the angle between the line that goes between the two charges and the direction of the electric field. We can also use this concept to calculate potential energy. So remember, work is equal to the negative of the change of the potential energy. So if we can calculate the work, we can use that to figure out what the potential energy is. So we learned last semester that work is equal to torque times the change in theta, or change in phi in this case. So I'm going to sub in my new torque relationship here, and I'm going to integrate between theta 1, or phi 1 and phi 2. For some strange reason, physics 2 uses phi, physics 1 uses theta a lot. I got to adjust my brain between last semester to this semester. So we're going to integrate in terms of phi. So the integral of the sine of phi is the negative cosine of phi. So that's what I have written here. I've evaluated here. And since work is the negative change in potential energy, I have to put a minus sign out here. And since we have cosine here, and we expect potential energy to be a scalar rather than a vector, this is actually a dot product here. So we can calculate the torque and the potential energy of a electric dipole in an external electric field, keeping in mind that those values are not going to be constant because it's going to rotate, and thus phi is going to change unless the value is going to change.